Let's consider the idea of amplitude modulating a signal which is a pitched signal. And we'll keep things simple, so I'll say it's specifically a sinusoidal signal. In terms of a block diagram, we could say that we have our source signal x of t modulated by a sinusoid at frequency fm. So again, the modulation means we're multiplying it by a sinusoid, and that produces the output signal y of t. Furthermore, let's say that the pitch signal has a frequency of f naught. That means the original spectrum x of f will correspond to a delta function located at positive f naught, and then another delta function located at minus f naught. So I'll put that down symmetrical about the f equals 0 axis. Now the easiest way to think about creating the output spectrum is as follows. Take the source spectrum, which I'm doing here with my copying and pasting. Take the source spectrum, shift it by amount fm. So that's what I'm doing here. My assumption is that the actual value of fm is less than f naught for purposes of drawing my picture. Then I copy the same exact spectrum and shift it by an amount minus fm. So I end up with a total of 4 spectral components. So one of those components is at f naught plus fm, the other is at f naught minus fm. And again, fm is our modulating frequency. Whatever amplitude we had, we needed to divide that in half, and that becomes a little more accurate presentation of that result. Make an interesting observation here. Notice that modulation generates new spectral components that didn't exist, and that's a hallmark of a nonlinear process. If it would have been linear, then when you excite it with a sinusoid, you just get another sinusoid, maybe with a different amplitude and phase, but still only a single sinusoid. So anytime you see multiple components being generated, that's a nonlinear process.